So yeah, thanks again for the introduction. My name, for anyone who doesn't know, Jacob Luhn. I'm a postdoc at University of California, Irvine. And we're going to be talking today about some projects I've been working on, looking at how we can characterize resolved stellar signals with EPRV era time series. And these are projects that I've been working on in collaboration with several of the collaborators listed down here below, as well as many others, especially NEID Science team members and EXPRES team as well. And so as we're thinking about the challenge of measuring masses of habitable zone Earth mass planets, we're in an era now where the challenge mostly is stellar variability. That's the next big hurdle for characterizing these types of signals that we're looking for. And it comes in a variety of flavors. Traditionally, the ones we think about are magnetic activity. These are things like spots, plage faculae that rotate in and out of view, typically on timescales of days to months, as well as long-term activity cycles on years. And this can have amplitudes anywhere from the meter per second level to well above 10 meters per second. Additionally, we often think about granulation, the surface manifestation of convection. And this operates on timescales of minutes to hours at amplitudes roughly a meter per second or so. And kind of the third source of variability that we talk about a lot is P-mode oscillations. And these are pressure-driven waves from convection that then travel throughout the interior of the star and create these surface deformations that then imprint themselves into the radial velocities that we measure. And this happens on a characteristic timescale, usually of order minutes for the dwarf stars that we often think about, and at amplitudes usually less than about a meter per second. And so there's a lot of different timescales, a lot of different amplitudes at play here. And so there are naturally a lot of different ways that we can try to attack this challenge. And just as a few examples of ways that we're doing this, I've listed them here, color-coded by the typical domain in which they operate. So in red, showing a few different time domain mitigation techniques. In blue, we're looking at things that operate on the spectra or sort of closely related, like CCF, cross-correlation functions. And then in green, also, we can use observational techniques to try to mitigate these sources of variability. And so we're left with a challenge of trying to understand how all of these different mitigation techniques perform on different types of stars and for different sources of variability. And I just want to highlight some results from Lily Zhao's work with the EXPRES Stellar Signals project that looked at a lot of these leading techniques, similarly color-coded, but at a much more granular scale by kind of the broad category or the broad method that they use to try to remove these effects. And this study was performed on a sample of 4 stars. And kind of the takeaway points are that for any given star, the methods kind of widely disagree on the amplitude and also the timescales that they attributed to stellar variability. And then from star to star, the performance of these methods wasn't consistent. So there was no one, best performing method that worked for all of these targets. And so this is pointing to this need to really understand how these methods perform for different types of stars and for different sources of variability. And so that outlines kind of the case for some of these high fidelity variability data sets where we don't necessarily know the answer in the back of the book 100%, but with well-resolved time signals where we sampled the sources of stellar variability, those timescales, we have very strong priors on the types of variability present. And particularly the time is ripe for these types of data sets. In the EPRV era, we have the requisite precision and stability to resolve very low amplitude signals. And along with that come new probes of stellar variability, things like line by line radial velocity techniques that just give us a different view of what's happening in the stellar spectrum. And again, yeah, this ultimately lets us probe these sources of stellar variability in new ways. And I'll specifically want to address the fact that we do have these high fidelity data sets for the sun. And again, highlighting some of Lily Zhao's work, more recent work here, I'm plotting or showing plots from her paper where she shows the agreement between these 4 different solar feed telescopes, where we see that they agree very well on this sort of low amplitude variability present in the sun. And so this gives us good confidence that our instruments are probing actual stellar signals. And these solar data sets are sort of setting the stage for similar detailed analyses, but beyond just the sun, we want these kinds of stellar data sets so that we can apply those techniques to other targets. So broadly speaking, hopefully setting the stage for this need for these types of data sets where we have well-resolved stellar signals. And so the focus of my talk is going to be in 2 parts. First, looking at resolved p-mode oscillations in a subgiant, HD 142091. And then the second part of the talk will be looking at magnetic activity on rotational timescales in this K-dwarf HD 26965. And I want to start by giving the takeaways for both of these points, so that hopefully will stick with you as we get to it later. And the first takeaway here for oscillations is that we'll see that the CCF morphology changes, so the line profile changes from oscillations, are driven primarily by pure Doppler shifts. And there's no strong dependence on either wavelength or line depth with these oscillation velocities. For the second part of the talk, magnetic activity, we'll see that these activity-RV connections really highlight the need for these well-sampled time series and the high cadence that is necessary for those. But then also a word of warning about using simple correlation metrics to diagnose or mitigate those effects. And then specifically on this target, we see time lags between activity and radial velocities that suggest either perhaps a more complex spot model or maybe an astrophysical time lag that isn't currently accounted for. So with that, I'll jump into p-mode oscillations in this subgiant target. And to motivate this a little more, I think many people on this call, and I would agree with them, might say that p-modes are a relatively solved problem for EPRV era measurements. And that's because we have a fairly well-established mitigation strategy, which is to simply average over the p-mode timescales with our exposure times. And specifically, this Chaplin et al. Result suggests an integer number of p-mode timescales. And for most targets that we're interested in, this reduces p-mode oscillations to about the 10 to 20 meter per second, or 20 centimeter per second level. But a downside here is that this requires a precise knowledge of the p-mode timescales ahead of time, as an incorrect exposure binning can actually increase your RMS, and this is especially problematic if you end up hitting somewhere between 1 to 2 p-mode timescales. Additionally, this is a method that's inefficient for larger telescopes that end up then spending a lot of time reading out rather than exposing. And these are telescopes that could otherwise achieve, high signal to noise with much shorter exposures. And lastly, less related to EPRVs, but still important, is this method becomes impractical for mildly or any evolved star, where these timescales and amplitudes of p-mode oscillations are much larger. And so if we're thinking about how we can resolve stellar p-mode oscillations to better study them, the way to do that is not to look at dwarf stars. It's very tricky to do with current instruments. I'll set aside KPF for now. Dan Huber gave a great talk 2 months ago about what we can expect from astroseismology with KPF, and that will certainly be exciting to see. But prior to KPF, if you want to resolve p-modes on stars, the way to do this is to look at slightly evolved stars, and that's for exactly those reasons, that the amplitudes and timescales are larger. And so you can see here on the right the typical time series from p-mode oscillations that you would expect for a sun-like star versus a subgiant. And so we can use the fact that these amplitudes are larger, the timescales are longer, to trace out these oscillations with really high fidelity on a subgiant star. So that's exactly what I did with target HD 142091 with NEID. We sat on it for almost a full night, interrupted just in the middle there with some intermediate cals, and we get really clean p-mode oscillation time series. And I just have to stop for a second and say that it's really nice when you get a data set and you look at it immediately and you can see a signal, and that's not something that we always get with EPRV data set. So this is certainly a fun data set to work with. And if we plot a GP fit to this time series, again, we see that it fits it really well. We get about a 25 centimeter per second residual RMS. So very cleanly resolved p-modes. And so with this, we hope to test some various diagnostics of stellar variability. And the first one that we'll look at is CCF morphology. So trying to distinguish shift-driven shapes, so pure Doppler shifts that are symmetric, from shape-driven shifts, which are sort of an apparent shift due to some perturbation to the CCF line change. And at the meter per second level, these are very hard to distinguish. These are exaggerated cartoons. It's hard to distinguish, especially just from the raw CCF. But we can look at the residuals to a mean CCF for all of our observations to see how those behave as well, comparing kind of this pure Doppler shift, which is, I guess, anti-symmetric, or however you want to describe it, versus the shape-driven, which still contains this perturbation, and these portions are unequal. And so we can perform that for our observations. And that's what I'm showing here. This is an animation, and when it plays, we'll see in this thick yellow line, we'll see the CCF residuals for the sort of binned over a few observations as we march through the night. And the individual observations will stack up kind of in this thinner line in the back, as compared to pure Doppler shifts, this greenish hue dashed line. And then on the right, we'll just watch the RV time series go by. And so we can see that for the most part, throughout the night, there's a portion maybe right about now where it doesn't, but for the most part, these RVs are introducing CCF shifts that appear to follow pure Doppler shifts. And so this is an interesting result. And we can look at this in another way, rather than looking at sort of an animation sense. We can look at the extrema, so all of the peaks and the valleys here, bin up over those observations and see that again we're getting a similar result, that these p-mode oscillations appear to be following pure Doppler shifts. And one last view of this, we can bin, instead of vertically at the peaks, we can bin in velocity space horizontally, and again just sort of showing that these are tracking pure Doppler shifts fairly well. Another way we can characterize CCF morphology is with line bisectors, and so we can look at those here. You can see again color-coded by radial velocity that there's a large gradient across this velocity space, perhaps indicative of a trend with RV. And in fact, there is a trend, and it's difficult to see here, but that trend that we're seeing is mostly explainable by a pure Doppler shift. So when we subtract out the median, or for all of these bisectors, we get a much tighter relation here between them, indicating that there's not a whole lot of variability in the bisector itself. And we can construct a mean bisector from this set and subtract that out to look at the residuals around that to further investigate, how much these line bisectors are shifting throughout the night. And that's what I'm showing here. And here there is a fairly evident gradient here. And to kind of jump to the conclusion, if you take these gradients or these bisectors and inject them into, say, a pure Gaussian CCF, and then extract the RVs, you get something or a time series that varies by less than a meter per second within the night. So there is some correlation with the oscillation RVs in the line bisectors, but not enough to explain fully the RVs that we're measuring. And so it's likely that this bisector is perhaps a second order effect. I think my phone just beeped at me, I'm sorry. Hopefully people can still see me, I think. The other thing that we can do is to investigate shape changes versus shift changes, is using a methodology called scalpels, which is some kind of neat math about how you can decompose symmetric shift changes using the autocorrelation of the cross correlation, decompose that into its basis vectors, and build back up the components that are attributable to shape changes. And so what I'm showing here is the results of a scalpels run on this data set, where the raw RVs are on the top, the shape-driven RVs are in the middle, and then if we subtract these shape-driven RVs from the raw RVs, we get the leftover, which is everything that's attributed then to pure Doppler shifts or shift-driven RVs. And I include this just to emphasize that the scalpels analysis really corroborates the story that what we're seeing here are shift-driven p-mode oscillations. And so this will be interesting if trying to develop techniques that can perhaps push beyond the 10 centimeter per second level for p-modes. We won't be able to rely on things like shape versus shift-driven if this result holds for more sun-like stars as well. Another diagnostic that we can look at, rather than CCF morphology, is the chromatic effects of p-mode oscillations. So Jared Siegel has run his line-by-line code on this data set, and we can take those thousands of lines, each with individual RVs, and bin them together across wavelength bins such that each bin has roughly equal RV weight. And I'm showing what these bins look like as a function of wavelength in a cumulative distribution function plot, just plotting the RV weight here. So you can see that the reddest bin is composed of a lot of lines that carry very little weight in the overall RV, and so it's a much wider bin. And if we bin the RVs of all of or average the RVs of all of the lines within a bin, we can plot the time series for each bin, run our GP fit, and compare how oscillations are being seen across the stellar spectrum. And that's what we're seeing here. So in this case, the wavelength bins, when we bin down all of the RVs, end up with typical RV uncertainty of about 2 meters per second here. And we don't really see a strong dependence on wavelength. There's perhaps a small hint of something, but nothing at a very large scale. And we can look at this in another way by taking the auto covariance of each of those bins time series. And so for each wavelength bin, plotting the correlation essentially as a function of time separation, where we see this characteristic p-mode timescale, roughly 70 minutes for this target. And again, very little deviation from bin to bin. And I'll just highlight this, this dashed line here, which is the auto covariance you would expect from a simulated time series. And as one last example of chromatic effects, we can just take the raw RMS of each bin RV time series and take a look at that RMS across wavelength. And again, seeing very little dependence here on wavelength, maybe a slight trend downward with increasing wavelength, but in the vast scheme of things, nothing that's reducing the amplitude by a considerable amount. And so again, thinking about either diagnostics or ways of avoiding or mitigating p-modes, it seems that p-modes are roughly constant across all wavelengths, at least in this subgiant star. We can run the same sort of analysis for an additional metric, the line depth metric. So we'll be seeing very similar plots to ones I just showed, but now thinking about the depth of each line rather than the wavelength of each line. And so again, running through the same binning process where we bin with equal RV weighting. The time series is here for each of these line depth bins. And a similar story. We see that the oscillation amplitudes are fairly consistent for all of our line depths. Looking again at the covariance, we see this same story. There's perhaps the shallowest bin behaving a little differently. We think that this could be due to microtellurics that are tracing the barycentric velocity for these very shallow lines. And in fact, they do show a linear trend within the night that is roughly consistent with the barycentric velocity. So that's a very plausible explanation for that. And looking at it kind of just in one takeaway plot, the oscillation amplitudes, or RMS, are fairly constant with line depth. So not a whole lot of variation here. Again, certainly nothing that can reduce p-mode oscillations by a factor of several. And so all of this kind of points to some interesting challenges if we're hoping to find diagnostics or mitigation techniques that could maybe improve beyond our current observational strategies. And sort of to summarize these P-mode diagnostics that we're seeing, again, dominated by pure Doppler shifts. There is some correlation with RV, so perhaps a diagnostic there, but these effects are minor and so aren't necessarily tied to the actual the RVs that we're measuring. And then lastly, we see no substantial reduction in oscillation amplitude with either wavelength or depth. So this was our P-mode time series, and really exciting time series, fun one to work with. I'm going to switch gears now from talking about P-mode oscillations to talking about magnetic activity. And so here now we're looking at this K-dwarf 26965. And this is a very bright target that has had a claimed planet that has now been fairly substantially shown to be likely due to magnetic activity. And so this is a really interesting target instead for its magnetic activity effects on the RV time series. And this is a target that's part of the NEID GTO target list. And so we get very good cadence and coverage over rotational timescales. And so I'll sort of walk you through what we've seen with NEID over a single semester. So this is the H alpha index of this star as a function of time over a span of about 150 days. And we see a really clean activity signal that's, again, very well resolved thanks to the cadence and sampling of NEID. And this activity signal is also seen in the RVs, maybe not as cleanly, but that's, I think, to be expected, given that the RVs, will also have contribution from things like granulation and oscillations as well. And this target isn't only observed by NEID, this is also on the EXPRES 100 Earths survey target list. And so we have EXPRES observations over the same time period. And those show remarkable agreement with those from NEID. And so that was also a very exciting thing to see, though I'll note that this didn't just pop up initially. This did take some effort to make sure that these values, both activity and RVs, were being calculated in a consistent manner. So Jared Siegel, again, ran his line-by-line code for both the NEID and EXPRES observations. And the activity indices here are derived using sort of a modified version of the NEID default pipeline. I'll also mention that the RVs have been median subtracted to fit on the same scale, and also have a roughly 60 centimeter per second amplitude trend subtracted over the course of the observations. That was fairly obvious by eye, just with EXPRES or NEID being systematically lower or higher at the beginnings and ends of the time series. And in case you couldn't see the signals here, if we perform Gaussian process fits independently to RVs and H alpha, we get these plots here, where we can now really see the correlation between activity and RVs. And just to highlight that, you can see this large correlation here as in the a cross correlation function, and I apologize for using cross correlation function here. Here, this is the cross correlation function between RVs and H alpha, so not related to CCFs of the spectra. But interestingly, we see that this correlation peaks with a time separation of a couple of days, 4 to 5 days. And so this indicates a several day time lag. And this isn't anything particularly new. This has been seen in in solar data. So Annelies Mortier has looked into the relative phase lags and time lags between activity indicators and the RVs. But even beyond that, a time lag is something that's expected from just a simple spot model. And so I wanted to walk through what a simple spot model looks like and how we can use that to explain some time lags. So sort of at the very basic level, our activity indicators are measuring the global magnetic field strength for these stars. And so as a spot rotates in and out of view, the activity indicators, in this case H alpha, shows a characteristic increase. In the RVs, we get a combination of two effects. The first is a convective effect, so the fact that these magnetic fields inhibit convection locally and reduce the overall net convective blue shift that we see for a star. And so you get this redward bump that is proportional to or falls in line with the H alpha activity indicators. Then the other component to the RVs is the rotational component. And this is analogous to the Rossiter-McLaughlin effect, where you will be blocking some of the blue shifted and then red shifted hemispheres from stellar rotation. And so you get this very characteristic red and then blue shift in the time series. And we'll note here that the sum of these two components then is a sum of a component that's proportional to the activity. So the convective component is proportional to activity, and the rotational component is proportional to its derivative. And particularly, you can see that the RV, the rotation component in the shorter dashed line peaks prior to its meridian crossing. So when you start adding in things like multiple spots and different spot sizes, you can get all sorts of interesting RV time series that perhaps look a little more like what we are used to seeing, things that are somewhat sinusoidal, quasi-periodic, et cetera. And that's led to the typical approach in Gaussian processes used to model the RV effect from activity. And in this approach, the H alpha is modeled as a GP kernel, and the RVs are a sum of that same latent kernel and its first derivative. And so this is directly modeling these convective and rotational components. And so if we turn back to this multiple spot configuration, we see behavior that looks very similar to what I showed for 26965. We see that the RVs and H alpha appear to be very well correlated, but the RVs are leading the H alpha time series, so indicative of a time lag between the two. And this is simply coming from the result of these two different components, convective component and the rotational component. Again, I mentioned how the rotational component peaks prior to its meridian crossing. And so that's why we see this, this typical RVs leading the H alpha time series. And depending on the relative contributions of the convective and rotation components, that time lag can be either increased or decreased. And just as an animation of how that effect works, as we are changing the relative strength between the two, the total RVs follow more like in this case, the rotation, or now we see it closer to the convective component. And so the total RVs, you can see where those peaks are shifting to either more closely match or match with a time delay the activity indicators. And when we plot up the expected cross-correlation function between the two, we can see quite clearly how this time lag in the correlation space is affected by this relative amplitude. And so again, these are apparent time lags. So there's nothing too astrophysical we can pull out of them, especially considering the degeneracies, as these amplitudes depend on things like the overall net convective blue shift of the star, which is very difficult to measure, the equatorial velocity, the spot contrast, a lot of different parameters here. But it's still a worthwhile endeavor to try to measure these time lags, either to use, as a to use for detrending, or just for measuring a more faithful value of the correlation between the two. You can see that if you didn't include a phase lag and just took the raw correlation between a time series of these two, in the case where there is a time lag, you can get correlations that are very small, or something that would suggest very little correlation, even though the two signals are directly related. And so in fitting this, you often need to fit some sort of model to it, and requiring interpolation in the time series, either a sinusoidal or a GP fit, and then computing the cross correlation between the two, and then fitting a peak in this cross correlation space. Instead, we've been working on a means of measuring the time lag simultaneously with our GP fit. And so we've been working on this sort of time lagged GP model, and I'll point you to Abby Burrows' paper that's currently under review, but should hopefully be out soon, within the next few months or so, where we go through some of the logistics of adding in this time lag here to our GP model. And so in this model, we're fitting a time lag hyperparameter, as well as a few jitter terms, one for the radial velocities and one for activity. And this is because we're fitting an RV model that is informed on the activity indicators. We don't expect that to capture all of the variability in the time series. Again, things like oscillations, granulation, and just other instrumental effects are going to end up being captured by this jitter term. So here's a fit using this lagged model. Again, you can really see this time lag here. It's very evident, especially looking somewhere around the 60-day mark, where you can see the RVs peak just before and the H alpha peaks just after. And so again, the green and the blue fits here are the same underlying GP signal, just multiplied by different exponents or amplitudes, and then the RVs are time shifted. And that shift that we get here is in fact about 4.5 days. I'll note the RV jitter that we measure is about 1 meter per second. And looking back to the independent GP fit that I showed before, you may notice that it seems that this independent fit is capturing perhaps more of the variability in this time series. And so potentially this lagged GP model is not capturing everything. And that's to be expected because this lagged GP model is an approximation to our simple spot model, where we've basically lumped these two terms together and said we can describe it with a latent GP that's time lagged. And so we don't necessarily expect it to perform that well. A better question is, how well does this model perform? And so in this simple GP approach, kind of the standard approach, we actually see fairly similar results that we saw in the lagged model. A better, or I guess a lower RV jitter value that's closer to what we might expect from the precision of NEID and EXPRES, but still overall, a very smooth time series that doesn't quite capture some of the high frequency variability that we saw. And especially thinking about or looking at the H alpha time series here and the fit. This independent fit that we had before seems to be capturing some more high frequency variability. And so it was interesting to then, or sort of as an exercise, was interested in looking at this perhaps better constrained H alpha independent fit, using that to determine the convective and rotational components, or in essence, what is the derivative of this green line, and how might that add together with the green line to produce RVs, and something that tracks what we're seeing. And so the derivative of this green line is shown here in the white line. And what you might actually notice is that it looks very similar to the RVs, just with a time lag introduced. So this was really intriguing when we first saw this potential lagged derivative model, where the RVs are potentially tracing the expected rotational component that we would expect from the H alpha time series, but on in this case, about 7-day time lag. And all I've done here is shifted this white curve down and moved it over. I haven't scaled it. And if we scale the amplitudes, again, this is just essentially normalizing these two curves. We get quite striking agreement between these two RVs just by including a time lag of about 7.5 days with the H alpha derivative, especially considering the way it's able to match some of these peaks and valleys. And so this led us to sort of a full model comparison, where we want to establish if this is just by eye a better fit, or if there is actually some statistical evidence here. So we go through a suite of models. The first is this lag approximation model. The second is kind of this simple spot model, the standard GP model. The third model allows for a time lag with this GP simple spot model. So it's model 2 plus a time lag. Model 4 is taking by extension the difference between model 1 and model 2, where we've approximated a time derivative as essentially just a time lag model, kind of extending that, thinking about whether what we're seeing, where maybe perhaps a lagged derivative model might perform better, could that be indicative of actually an additional time derivative component? So this one's motivated more mathematically than, say, physically. And then our final model is exactly what I showed on the previous slide, which was a lagged derivative only model. And so it's very similar to model 3, but we've set A00 to 0. And the reason for that is because in practice, it's difficult to get this model to, given our bounds on these parameters, it's difficult for the model to prefer very low amplitudes here, just because we've set hard bounds at 0 to avoid bimodal posteriors from like reflection symmetry about positive and negative. So just kind of summarizing our results, we've thrown this through our nested sampler to compute accurate evidence ratios. And our model 5, this lag derivative model, is the best performing model with all of the rest of these values computed relative to it. And I've taken the absolute value here, so all we care about is the magnitude difference. And we see that, yeah, model 3, as expected, this is very similar to model 5, and so not necessarily a strong favoring of model 5 over model 3, but compared to the other models, model 5 is within the realm of suggestive or substantial evidence, maybe not quite at the strong or extreme, extremely favored. And so our model 5, this is the resulting time series that we get. And again, it has, we're able to fit a lag parameter, in this case about 6.5 days. And what this means is difficult to sort of internalize what we're seeing. But if you take, say, a minimum here in H alpha, the derivative at this point is 0. And so this point in the H alpha time series corresponds to the RVs crossing 0 here about 7.5 or 6.5 days later. And so this is really intriguing. We'll also note that the RV jitter that it gets is perhaps more on par with what we expect from NEID and EXPRES precision. And so, yeah, this an intriguing result. I'll just, for completeness, share kind of all of the model time series where we can pick out some similarities and differences between a few models. But thinking about some of the implications, and I won't do too much more than a few musings. So the implications, if this is actually a physical model of what's happening on this time series, we're seeing that the instantaneous derivative of the activity time series predicts the RV behavior 6.5 days later, which is very interesting. And I point this out more as a means of highlighting the fact that these activity time series and well-sampled activity time series have very strong predictive power on the RVs under all of these models. And so I just want to highlight the opportunity here, beyond EPRVs for the just kind of standard precision radial velocity instruments that can still get very high signal to noise activity time series. And so there is an opportunity for those and a role for those types of instruments. Additionally, thinking about a little more physically what could be explaining what we're seeing, perhaps complex spot geometry or configurations, either number, sizes, distributions, could perhaps explain what we're seeing. And we're working on, pardon the pun, spinning up some of these simulation codes to run through our full model comparison to see if we can get similar results where this lagged time derivative performs better. But thinking a little more astrophysically about, if this model is true, what could this be telling us about what's happening on the star? And under a simple spot model, we are assuming that kind of the flux effect, the magnetic effect, and the RVs are all coupled. And so perhaps, one of those in this chain is being not necessarily decoupled, but pushed out of phase. And just as one possible hypothesis, you could perhaps explain this with some sort of magnetically bright, but otherwise photometrically quiet features that always precede dark spots, which is maybe a little convenient to claim, but does evoke some similarities to things like what we see with sunspots. So for instance, Hale's law of spots appearing in pairs with opposite polarity. Also similarly, Joy's law, where those paired spots, typically the one that precedes the other is closer to the equator. And so perhaps something similar on a star, maybe combined with viewing angle, could be a possible explanation. And it's something we're still thinking about. So to summarize this, this section of activities in this very interesting target, again, sort of this word of caution for simple correlation metrics. We see that it can sometimes, in the presence of time lags, be a raw correlation doesn't tell the full story. And some of these GP lag techniques might be better indicators of whether you're seeing an activity-induced signal. And then in this particular case, this suggestion of perhaps a more complex spot model or some astrophysical time lag that's not accounted for. And we're close to the hour. I'll just final slide. Just looking ahead, what does this tell us? So we are in the midst of full spooky season. And so when I look into my crystal ball, what I see is a lot of stellar variability. And really that excites me. I think a lot of these instruments are going to give us really, really fun data sets to play with. And I'm particularly excited for the synergy between a lot of these instruments that are coming online. And again, highlighting that this doesn't have to be just limited to EPRV spectrographs. And lastly, I want to sort of shout out this Standard Star working group that Jen is leading. I think that will be a really good opportunity to perform some of these things. There's the evergreen debate of whether these are intended to be looking at instrumental diagnostics versus stellar variability diagnostics, but either way, we will get both. And so I'm really excited for what will come from that. And with these individual types of case studies, how we might apply those to new data challenges and learn about potentially, on a source by source basis, how our mitigation techniques perform. And so, yeah, I'll stop there and go ahead and take any questions. Thanks.
Thank you for a wonderful and beautiful talk, Jacob. This is one of the times when I'm very excited that we record these and save them to our archive, because I already know I'm going to send students to this in the future for when they want a grasp of how stellar activity messes with our radial velocities. I'll see as many clapping hands emojis in the Zoom already. I invite people to raise their hands and ask questions if you can stay a couple minutes after the hour. And Sukanya, I see your hand up, so go right ahead.
Hi, Jacob. Thanks for a really nice talk. So I had a few questions, and I'll just go in the order in which you presented. For the subgiant star, what was the effective stellar jitter for that source? And what was the RV precision for the data sets that you were talking about?
Okay, good questions. For the subgiant, in terms of stellar jitter, I guess there are a few different ways I could answer that. In terms of treating stellar jitter as all astrophysical sources, and if we take a straight RMS, the amplitudes there are something like 5 or so meters per second. So, and that's typical for some of the more evolved subgiants, which I think this is one of. Your second question was about typical RV uncertainty. Is that correct, about the instrumental?
That's right. Yes.
Yeah. Yeah. So for both NEID and EXPRES, sort of expect somewhere in the 30 to 50 centimeters per second. For a longer base time series, like the magnetic activity target, probably larger just from instrumental drifts and calibrations and things like that. For the subgiant target with NEID, the intra-night precision is expected to be much better than over necessarily many months, and so something like what we are seeing with the residuals, about 25 centimeters per second. I guess the photon noise limit there was something below that. These are all very bright targets, or these were both very bright targets, and so the sort of raw out of the pipeline RV uncertainty, I think for perhaps both of these, was in the 18 to 20 or so centimeter per second level.
So I had one more question. Sorry, you said in the second part of your talk for the dwarf star, you said the instantaneous derivative of the activity time series predicts the RV behavior some number of days later. Is this? How do you think this might be a more generic result? Have you looked at this?
Yeah, and that's another great question. So I haven't applied this to many other stars. I have applied it to solar data, and solar data, we know the sun pretty well, and we don't see that that there's evidence. I haven't done the full model comparison, but you can explain, at least during a portion, I think maybe a year and a half ago, there was a very clean activity signal in the star over, or in the sun over a few rotation periods, and in that case, you can pretty much explain away the RV effect just with a pretty much linear detrending. So in that case, the RVs are tracing the H alpha almost exactly. There's a very strong correlation there. So there's really no need for that. As far as other stars, that's something I would like to test. Getting targets that with sufficient cadence and well-resolved activity signals is a difficult task, but I'm hoping with some of these efforts, especially Standard Star Working Group, we might be able to do some testing of that.
Yeah, I promise we're going to try and fit at least a couple of stars with interesting activity signals into the Standard Star list.
Yeah, I'll do my best to. Oh, I was just gonna say I'll do my best to push for 26965. It's quickly becoming my favorite target.
Be a good advocate for it. Yes. Megan, I see your hand. Go right ahead.
Yeah, great talk, Jacob. A question about the P-mode oscillations, and especially your line-by-line analysis of that. Just thinking about it naively, if modes are propagating radially through the star, and you're looking at lines of different depths, you should see like a gradient of phase shift with the depth of the line, right? Would you be sensitive to that? Have you looked?
Yeah, so that was actually part of the motivation for looking at line depth, was hoping to trace, how these P modes are propagating through the atmosphere. Yeah, if there are things like phase shifts between different depths, and it's not something that we're seeing. I haven't done that analysis, but it would be interesting to do, say, a cross correlation between all of the different bins. I mean, just by eye, the time series, they match up very well, and so But eyes can be deceiving, so you can run that test and take a look. The other thing is that line depth isn't a direct one-to-one of height, and so another thing I'm interested in is the actual formation height temperature, similar to Khaled Al-Mullah's work, and running and binning from actual formation height. But that's not something that I've done yet.
Cool, thank you.
Okay, new hand, Sukanya?
Yeah, I think it's really fast. So I was a little bit surprised that, for your different GP models that you applied to the dwarf star, right? Your effective stellar jitter can sometimes be different by more than a factor of 2, or am I just misremembering?
Yes, that's correct. I mean, in that case, the jitter is more of a diagnostic of how much variability the model is able to capture. And so it's more of a diagnostic of that rather than pure stellar jitter. So not necessarily something to write down, but ultimately, measuring a jitter for any star comes down to how well we think we've modeled out things that aren't jitter. And really, if we're thinking about jitter, I guess in the sense of a stellar jitter term for a star, you would likely not even apply a GP model, because you want that jitter value to capture something like activity modulation, and so you would just take potentially the raw RMS of that. But yeah, I guess in this case the jitter is more accounting for non-activity jitter.
Okay, Eric, I see your hand up. Go right ahead.
Could you comment on the different potential stellar activity indicators and to what extent they show similar strengths of correlations and lags and models being favored, or if everyone is its own special snowflake?
Right. So for NEID, we get quite a few activity indicators. And for this target, 26965, a lot of them correlate very strongly with each other. And so I haven't necessarily performed those results, but I would imagine very similar results for things like calcium H and K. I think the infrared triplet, or at least one of the infrared triplets, was very well correlated. And so that's something we saw. The challenge was in kind of using this, I guess, hypercadence combined NEID and EXPRES time series. The express signal to noise at calcium H and K wavelengths was too long, didn't go far enough to extend to the infrared triplet. And so really we were left with just H alpha. And so that was kind of what we've looked at. It would be interesting to also look at things like the CCF full width half max, bisector inverse slope. But again, those are things that weren't natively in the pipeline and haven't spun up between the two instruments yet. So those would definitely be something interesting to look at. But I guess short answer is NEID shows a lot of similarity between many of the activity indicators, and so I would expect similar behavior.
Thanks.
Okay, we're far enough over the top of the hour that I think we should probably wrap things up there. So I will say thank you again to Jacob, and remind folks that we'll be back a week later than normal, so November 30th next month, so that we avoid the Thanksgiving holiday in the US with Ashley Baker and Joe Tufts. And so I look forward to seeing many of you there. Thanks everyone for calling in, and catch you in November.